Hi there, Mr. Sutton here, bringing you the AB Calculus 615 Extra Practice number 5 solutions on integration with respect to the y-axis. For this problem, we want to know the area of the region in the first quadrant, bounded on the left by this x equals graph, and on the right by this other x equals graph. Well, this is a graphing calculator question, so let me try to graph out this situation and see what we're looking at. To start this process, I'm going to enter the functions they just gave me in my y equals as x functions. So instead of 5y, I'm going to enter y equals 5x. And instead of y to the fourth plus y squared, I've got x to the fourth plus x squared. So in order to the problem is, let me do zoom 6 first off to show you what this looks like. So here's the two functions. Well, here's the inverse of the two functions that they actually wanted me to graph. This isn't quite going to cut it if I want a true visual representation. If I want to know what this really looks like, I'm going to quit out of there. Let me actually go back into my y equals, and I'll unselect those, so I'm not actually graphing those. Now let me quit out. I'm going to draw the inverse of those, and that'll actually end up giving me the functions they originally gave me. So I'm going to go to my draw menu. That's going to be second program. Option 8 gives me draw inverse. And I'm just going to do alpha trace and do y1. So I'm basically drawing the inverse of my y1 function. So here's that sideways looking graph that they wanted me to actually draw. And let me just quit out of that and yank my input from before. I'm going to do draw inverse for y2, alpha trace y2, and press enter. So this is what I'm really looking at. And by the way, while I'm at it, I'm going to rename these. This one I'm going to call f of y. This other one I'm going to call g of y, just so I don't have to do a whole bunch of writing to refer to them quickly. So when I graph out f of y and g of y on my calculator, this was the picture I got. So I basically need to figure out the area of this little sliver of a region in here. And since I've got my functions in terms of y here, I'm going to have to integrate with respect to the y-axis. I could try to change these to y equals x functions, but it's going to be a little bit tricky on this one, for example, to try to isolate y. So really it's y integration or nothing on this one. To do that, I need to know the limits of integration, and I also need something for my integrand. To get my limits of integration, I'm going to have to figure out the intersection points here. I know that at the bottom we're intersecting at y equals 0. This other intersection point, though, I'm not so sure about. So to find that other intersection point, I need to know where f of y and g of y equal each other on the graphing calculator. And that's going to be a little bit tricky because I can't actually set these things equal to each other or find intersections with drawings. This is a drawing, not an actual function. To find intersection points, I have to graph this as a y equals x function and be a little tricky about it. Well, let me show you. So back on my grapher, I'm going to quit out of there, and I'm going to go to my draw menu, and I'm going to just clear those drawings out. I don't want them anymore. Now I'm going to go to y equals, and I am actually going to select those two graphs again and actually graph them out. What I'm going to do is I'm going to find out where these two inverse graphs intersect. And the x values where these intersect are going to correspond to the y values where the real graphs intersect. We already know we intersect at 0, 0. So that's an x value of 0 and a y value of 0. If I find the x value where these graphs intersect up here, that'll tell me the y value where we intersect over here. So let me do second trace. Option 5 for intersect. Let's move my spider a little bit up the way here. Press enter 1, 2, 3 times. And those are intersecting at x equals 1.5160 if I round it off. So there's this. Now I know that really means y equals that number. And I'm also, while I'm at it, while I'm writing this down, I'm also going to call this p from now on. This is just the constant p because I don't feel like writing that over and over again. And I'm also going to store that on my calculator. So let me quit out of there, and I'm going to press the store button, and that's going to store what I just got as, let me do alpha p, alpha button, there we go. So now I can call that up whenever I need to. All right, I'm going to need it right away because I'm going to now take the integral from 0 to p of, and now I have to do right minus left. Now the good news is I've already got these in terms of y. So the right function, and they even told me which one was on the right. It's this 5y one. So I'm going to do 5y minus this other function here, basically g of y minus f of y. That's why I renamed them, so I didn't have to rewrite everything. And that's going to be with a dy. So this is the setup that we're now going to do on the calculator. To do that on the calculator, I'm going to be a little bit tricky again. Let me do Math 9 to pull up an integral, so nothing tricky there. Limits of integration are going to be 0 and alpha p. Now keep in mind these are y values theoretically. And I'm going to do g of y minus f of y. This is where I get a little bit tricky. So I have these entered as functions of x, or functions of y in terms of x. So I'm going to use, for g of y, I'm going to use my y2, because if you look back here, there's where I entered, like this is kind of like g of x right here. But I'm going to use this anyway, even though it has an x in it, to kind of stand in for this g of y. I'm going to use y1, even though it has x's, to stand in for this f of y. And it's actually going to work out in the end. So going back to the main screen, filling things in. For gy, I'm going to do alpha trace. And let me pull up y2 out of that menu. And then we're going to subtract alpha trace y1 for f of y. And the reason it's all going to work out, even though these two functions have x's instead of y's in them, is I'm going to write dx right here. So that's going to force my calculator to treat that just like this integral is treating everything in here. So pressing enter for that, we end up with 2.983. So the journey's over, choice A. For this no calculator problem, M is the region in the first quadrant bounded by y equals 3x plus 2, y equals x plus 2, and the vertical line x equals 3. We want the volume of the solid generated if M is revolved around y equals 1. I'm going to need to graph all this out. I can't really make heads or tails of what all this means if I don't have a picture. So here's my x and y axis. The line 3x plus 2, I'm not going to be super accurate, but we're starting above the y-axis, above the x-axis, and we have a positive slope, so there that is. And x plus 2, it's going to be the same y-intercept as 3x plus 2, but a less steep slope, so something like that. We have the vertical line x equals 3 going through both of those. So this gives me the region M that they're talking about. And I want to revolve this region M around the horizontal line y equals 1, which, since this is the y-intercept 2, that horizontal line is going to be down here. And it does make a little bit of a difference what side we're on. Okay, so how can I do this? Well, for one thing, I can integrate with respect to x. This is just a top-to-bottom kind of situation here. We're going over a horizontal line, so that'll make things a little bit easier. For my limits of integration, going from left to right, on the left side we're going to have 0. On the right side, this was the line 3, x equals 3. So we're going from 0 to 3. All we have to figure out now, since we're talking about volume, is what area formula we're going to be integrating over this interval from 0 to 3. Well, since it's a solid of revolution, that means we have to choose between our two circle shapes, discs and washers, pancakes and donuts. Because we have this gap here between the M region that we're revolving and the axis of revolution, that means we have to use washers for this. So I'm going to write a of x equals pi times big R squared minus little r squared. Big R squared, that's the distance from my axis of revolution to the further away part of the bounded region. The further away part is represented by this 3x plus 2 function. So that's going to be 3x plus 2 minus this value down here of, let's see, this was the line y equals 1. So 3x plus 2 minus 1, that expression gives me big R. And I'm going to be squaring that, and I still have that pi outside. Now we're going to subtract little r squared. So little r is going to be this inner part of the bounded region minus that horizontal line of 1, the distance here. So this is going to be x plus 2 minus 1, and we're squaring that and subtracting. All right, it's just about time to integrate this thing. There's just one problem. This is a no calculator problem, so I am going to be integrating this by hand. Do I really want to take the integral of this? Probably not. Let me try and clean this up a little bit to make my life a little easier. So one thing I can do in here is I can combine these numbers. This is really 3x plus 1. And then if I square that parentheses, I've got 3x plus 1 squared. I'm going to use a squared plus 2ab plus b squared. So this is going to be 9x squared, and I still have that pi out there. 9x squared, and then I have to multiply the 3x and the plus 1 and double that. So I've got a 6x in there. And then the 1 that I have in there squared is just 1 if I square that. Over here now, this is really x plus 1 squared. And everything is getting negated because of this minus out here. So this is going to be, it would have been x squared plus 2x plus 1 normally. But now it's going to be minus x squared minus 2x minus 1. Cleaning this up still further, the plus 1 and the minus 1 cancel. We have 9x squared minus x squared, which is 8x squared. And 6x minus 2x is going to be 4x. So this is what we're going to take the integral of. And again, we're going from 0 to 3. So integral from 0 to 3 of that stuff. And I'm going to pull this pi outside as well, make my life even easier. So I'm doing a lot of things to try to decrease the arithmetic I have to do with this integration. But at this point, there's nothing else for it. I have to take some antiderivatives. I have to plug in 3 and 0. So antiderivative of 8x to the second, that bumps up to an exponent of 3. Dividing by that, I've got 8/3 x cubed. Still have that pi hanging around outside. And now this bumps up to a 2. Dividing by that, I have 2x squared. Integrated from 0 to 3. So now I've got a pi, and opening a huge parentheses here, I've got all of this stuff with 3 plugged in, minus, still inside that parentheses with the pi outside, minus all this stuff with 0 plugged in. I do have to simplify this. That's the bad news, because I'm matching a multiple choice. The good news is all this stuff with 0 is just gone. So it really is just this first bracket times pi. So I've got, let's see here, 3 cubed is 27, divided by 3 is 9. 9 times 8, that's going to be, what is that, 72? And then this is 2 times 9, which is 18. So we have 72 plus 18, which is 90, times pi gives us a grand total of 90 pi. So that's answer choice B. For this problem, R is the region bounded by y equals 2x minus 2, y equals 2, and the vertical line x equals 1. We want to know which gives the volume of rotating R around the vertical line x equals 1. So let me get a little graph of what's going on here. So I have 2x minus 2. That's a y-intercept of negative 2, slope of 2. It's a line looks something like this. We have the horizontal line y equals 2. That's going to be somewhere up there. And then we have the vertical line x equals 1. Now, interesting to note, since you're starting down 2 and going up 2 over 1, at x equals 1, which is where your vertical line is, that's actually also where this slanted line hits the x-axis. So we're actually intersecting right there to give this nice little triangle shape. So this is the shape that we are now revolving around the vertical line x equals 1, which is the left border of your bounded area. Since I'm going around a vertical line, I'm integrating with respect to y, which means that I have to convert this function right here into an x equals something with a y in it in order to use it in my y integration. So I can do that if I add 2 and divide by 2. So this is going to be x equals y plus 2 all over 2. And now I also have to decide, since I'm doing a solid of revolution, I have to decide, am I using pancakes or donuts? Am I using discs or washers as my area that I'm going to be integrating? I also need to know what my limits of integration are while I'm at it. Let's talk about limits of integration first. That's an easy one. Since we have a nice little picture to go on here, we're going to be going from bottom to top. So our bottom value, bottom y value at the tip of this triangle is just 0 for y. Up here, this was the line y equals 2, so we're going from 0 to 2 then. Now we need the area formula here. Since I have, let's see, I'm going around the line x equals 1. Since that is actually one of the boundaries of my bounded area, that means that my bounded area is flush against that. There's no gaps. So I can use disks for my area formula. So I'll write a of y equals pi r squared. The radius is just going to be the distance between my axis of revolution and the other side of the bounded region. That's an x distance, a horizontal distance. And that's just going to be this function right here minus however far we already are over from the y-axis. So basically y plus 2 over 2 minus 1. That's what I'm going to be squaring inside that pi r squared situation. So now taking the integral of this thing, again I'm going to be going from 0 to 2, and I can take this pi outside of the integral. I always do that so I don't have to mess with it inside. So we just have all the rest of the stuff inside now with a dy. And does that match any answer choices? Well, we need 0 to 2 for the limits of integration. So that means we're picking between choices B and D. And I don't want things individually squared like they are in D. So I'm going to go with choice B then. I just want everything being inside a squared parentheses being subtracted inside one squared parentheses. So B it is. For this one, we have this R region that we're trying to find the area of. And this is bounded by the graphs of x equals y squared and x equals 2y. So I'm going to be integrating with respect to y on this one. Seems like the way to go since they already gave me these functions as x equals functions of y. But to do that, I need to get my limits of integration. So because I'm going with respect to y, I have to go from bottom to top. So my limits of integration are the bottom and top y values. On the bottom, we've got 0. On the top, I'm not really sure. This looks like it's probably 2. To really be sure, though, let me just set these two things equal to each other. So y squared equals 2y. Now let me just test out both of those. If I plug in 0 like I think that intersection point is, 0 squared does equal 2 times 0. So that's good. And if I plug in 2 like I think the upper limit should be, 2 squared does equal 2 times 2, so that also works out. All right, so our integral is going to be from 0 to 2. What's going to be inside? Well, we have to do left minus right, or actually right minus left. Further away from the y-axis minus closer to the y-axis. So that's going to be 2y minus y squared. So I have the integral then from 0 to 2 of 2y minus y squared dy. I have to do this by hand because this is not a calculator problem. So taking some antiderivatives, this first one, this is going to be, let's see, this is going to be a y squared. Dividing by 2, we have just 1y squared. This bumps up to a 3 exponent. Dividing by that, we have negative 1/3 y cubed. Evaluating that from 0 to 2, I have all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. And going from left to right, I have to simplify this because my answer choices are simplified. I'm going to have, let's see, 2 squared is 4. This is going to be minus 8 over 3. Everything over here with the 0 is just gone. So we have 4 minus 8/3. This is really 12/3 minus 8/3, which is just 4/3, which is just answer choice B. For this problem, we're given this R region here between the graph of y equals ln of x and y equals 1 and the vertical line x equals 1. We want to know which of these gives the volume of the solid generated if I revolve this around the vertical line x equals 1. So I'm going to have to integrate with respect to y, which the answer choices make abundantly clear. For that reason, I'm going to take this function y equals ln of x and express this as x equals something with a y in it. So I'm going to rewrite this as x equals e to the y if I raise e to both sides. And now I can go ahead and get an area formula that I'm going to integrate. I have to figure out what kind of area formula I want, though. Since the axis of revolution, x equals 1, is one of the boundaries of my bounded region here, since there's no gaps, since this is flush against the axis of revolution, I can use disks on this one. So I'm going to go with a of y equals pi r squared. The radius is just the distance between my axis of revolution and this other boundary of the region. So that's going to be a distance of whatever this function is minus the 1 to get that distance. So that's going to be e to the y minus 1 for r. And plugging all that in, I've got the integral from, well, I have to go from bottom to top here. So I'm going to be going from the y value 0 to the y value 1. I'm bringing my pi outside just to make my life a little bit easier and also to match these answer choices. And inside now I've just got e to the y minus 1 squared dy, which is going to end up giving me, let's see, this looks like choice C. For this calculator-based free response problem, we're told that R is the region in the first quadrant enclosed by y equals arctan of x and y equals x squared, as shown above. So between these, x squared is the lower function, and arctan is this other function here, although it's kind of hard to tell just by having only a small piece of these. What we want to do for our first task is find the area of R. So to make my life a little bit easier, I'm actually going to name these functions. I'm going to call arctan of x f of x, and I'm going to call y squared g of x. So now I can just refer to those quickly. And if I want to find this area here, I'm going to need to take the integral of basically top minus bottom from left to right. So I need to know where these functions intersect so I know what my left and right limits of integration are going to be. Let me graph these out to see where f of x equals g of x at what x values. So let me go to my y equals. In y1, I've got my f of x function, which arctan and tan inverse, or second tan, are really the same thing. In y2, I've got x squared. That's my g of x function. I'm not really sure which window I should use, but based on what I see here, these are kind of zoomed in. I'm thinking I can get pretty close and still find that intersection. So let me do zoom 4 and see what we come up with. So there's arctan. There's x squared, and yeah, I can get way closer. Let me actually make my window between, let's go from 0 to probably 1.5 is even too much, but let's start with that. Zoom 0 now, zoom fit, to get a really good look at these two functions. So there again is arctan. Here is x squared. Clearly these things are intersecting at 0, but let's see what this other intersection point is going to be. So to find that, I'm going to do second trace, and then option 5, intersect. And my spider's almost about there, so let me just press enter 1, 2, 3 times. And that's about 0.8336. So here's the graph that I just looked up. I mean, I know these things are intersecting at 0, and if you plug 0 into both of these, arctan of 0 is 0, 0 squared is 0, so 0 works. But we also have this 0.8336 number, and I'm actually going to give that a name. I'm going to call that P. So now I can use P instead of rewriting this constantly. I'm actually also going to go on my calculator and store that value. So let me quit out of the graph, and I'm going to go to stow and click alpha P, or whatever letter you want to use. Doesn't have to be P. Press enter, and now I've got that until I decide to change it to something else. So back here, I want to take an integral now. I'm going from left to right, so 0 to p of, and I have to do top minus bottom. So the top function, again, that was arctan, that was the f of x function. Bottom was g of x, x squared. So I've got f of x minus g of x dx, and I'm going to do that piece on the calculator now. So here we go to plug this in the calculator. I'm going to do math 9 for integral. We're going from 0 to p, so alpha p. And in here to do f of x minus g of x, I'm going to do alpha trace, pull up y1, that's where I stored f of x, minus alpha trace, pull up y2, that's where I stored g of x. I'll put a dx over here, press enter, and that area is going to be 0.122. Our next task on this one is to find the volume of the solid generated if R is revolved around the x-axis. We already have our limits of integration. It's going to be 0 and that p number, which was like 0.8 and some change that I found in part A. I already defined it in part A, so I'm going to use it again here. But I need an area function now. When I'm doing a solid of revolution, I have to choose between disks and washers for my area that I'm going to integrate. Am I taking slices of pancakes or donuts? That's what I need to know. Since I have this gap here between the bounded region and my axis of revolution, that tells me I need to use washers, donuts. So I'm going to start with a of x equals pi times big R squared minus little r squared. Big R is going to be the distance from my axis of revolution to the further away curve of the bounded region. That further away curve is f here. So the distance from 0 to f is just going to be f of x. So this is pi times f of x squared minus, and now little r is just the g function, the closer curve there. And I'm squaring that as well. So in the calculator, and notice I called this a sub 1 because I've got another area formula coming up in part C that I don't want to confuse with this one. So now to get the volume, I'm just taking the integral from 0 to p of a sub 1 of x dx. Let me do this on the calculator. Just to do this a little more cleanly, I'm going to define this a sub 1 of x function in my y equals as y3. So this is just going to be pi times, and I'll open a parentheses here, I need f of x squared, so that's going to be alpha trace y1 squared, because that's where I stored f. And I also need to subtract g of x squared, so let me just do alpha trace y2 squared, and close that parentheses now. Let's quit out of there now, and I'm just going to take the integral, so math 9, from 0 to alpha p of y3, where I just put my a1 function. So alpha trace y3, put a dx in there, press enter, hope for the best, and my volume is 230 if I round that off. There we go. For the final boss battle on this free response, they're telling us that region R is now the base of a solid, and for the solid, each cross-section perpendicular to the y-axis is a rectangle whose height is twice the length of its base in region R. Find the volume. So essentially, we have these rectangles popping out of this bounded region in a three-dimensional fashion, and these rectangles are perpendicular to the y-axis. So I'm going to have to integrate with respect to y on this problem. Knowing that, I'm going to go ahead and rewrite these two functions in terms of y. So this arctan function, I'm going to get x by itself now by taking the tan of both sides, and I'm going to write x equals tan of y. But I'm not going to write that. I'm going to actually write f of y equals tan of y. And so now I can just refer to this as f of y. And then let's see, this other one, y equals x squared. I'm going to rewrite this as x equals g of y equals the square root of y. So basically just solving for x on both of those. Now, one other thing I'm going to need is I'm going to need to know, since I'm integrating with respect to y, I need to know new limits of integration. I'm no longer going from left to right, so I can't use p anymore for my upper limit of integration. I have to use the y value at this intersection point. So I need to know then where f of y and g of y intersect, or I need to know the y value of intersection of f of x and g of x, either way. Let me find that on the calculator now. So there's a lot of ways to do this. To make my life as easy as possible, because I don't need them anymore, I'm pretty much just going to clear out all these other functions that I put in for earlier problem parts. And I'm now going to put in these other functions. So I'm going to have tan of x, which really means tan of y, but the x value I get out of this is going to be the y value I would have gotten from the other function. And then I'm also going to write square root of x, which we understand really means square root of y. And then I'm going to go ahead and graph these to see where they intersect. So let me just do zoom 4 on this one. I assume these are going to be pretty close together. So we have an intersection point here of how much? Let me do second trace again, and then option 5 for intersect. Let's move the spider up to that little itty-bitty intersection spot. Enter, enter, enter. And that comes out to 0.69, 49. So there it is zoomed in. So that's actually a y value that these things, it's whatever the input value to these functions is. So this is going to be y equals that. So 0 is the other one, and then y equals 0.6949. Now I'm going to call this point Q on my calculator and on the paper. Let me go back actually and quit out of there, and let me store that value that I just got as alpha Q. So now I can pull that back up as needed. All right, so I've got a few things here. I've got my limits of integration. I'm going from 0 to Q, but now I need the area formula that I'm going to integrate from 0 to Q. Well, we said we're dealing with rectangles. So in general, I can say a of y equals base times height, but it'd be nice if I had only one variable going on. They did say the height was twice the length of the base. So this is really b times 2b, which is just going to be 2b squared. And now I need to redefine the base in terms of y. The base of these rectangles is just going to be the distance from one end of the bounded region to the other, from left to right. So to get that horizontal distance, all I have to do is do the right function minus the left function. So that's going to be, let's see here, g of y minus f of y. So now I'm going to have the integral from, so that's what I'm squaring inside there instead of b. So now I'm going to have the integral from, we said, 0 to q of this a sub 2 function, a sub 2 of y dy. Let me do all that on the calculator now. To make my life a little bit less cluttered, I'm going to actually write the a2 function in my y equals. So this is really 2 parentheses, and I've got g of y, so that's alpha trace y2, and this is the y2 that I redefined here in part C, not the one from earlier, minus, let me do alpha trace y1 for f of y, and all of that parentheses is being squared, so that's now my a2 function as y3. Quitting back out to the main screen, I'm going to do Math 9 integral. We're going from 0 to q this time, so alpha q. And y3 is where I defined a2. And although I have all of that stuff defined in terms of x, it's going to be okay. It's going to work out because I'm going to put an x right here. So now my calculator is going to treat everything I've done there the same way that this integral would be treating everything I've done over here. So pressing enter, that comes out to 0.0, I guess 50 if I round to 3 decimals.